Okay, welcome class to Physics 203, class number 11. This class is on de Broglie waves and scattering, and it's our first section on the further development of quantum theory beyond the Bohr atom. And we'll first look at X-ray scattering, which is a classical phenomenon that was proved to be very extremely useful. And then we'll look at a really interesting and almost bizarre idea by a Frenchman named Louis de Broglie about the nature of electrons and how that led to the possibility of electrons being used to scatter like waves. Um, Without further ado, let's get into the material. In the X-rays were discovered in 1895 by Henri Becquerel, but they proved hard to reflect, like light rays can reflect off of mirrored surfaces. But if you try to reflect X-rays off of a regular mirrored surface, it won't form a coherent image. And this led to the conclusion that they were, this and other experiments led to the conclusion that they were electromagnetic radiation, but of very short wavelength. Because they were of such short wavelength, irregularities in the surface of the mirror would cause them to reflect in random directions and not form a coherent image. So X-rays were known by this and other experiments to be electromagnetic radiation of short wavelength. And a German physicist named Max von Laue in the 1910s had the idea that with wavelengths of 1 nanometer, they might be able to diffract from atomic lattices, because it was known that atoms were on the order of size of a nanometer. And so this is, in fact, a setup of how that would worked, some of the initial experiments and indeed current experiments. There's an X-ray tube here, and electrons would be decelerated rapidly enough to give off X-rays. The X-rays would come through optionally a lead screen to reduce their intensity. And then a solid, an atomic lattice here, would be interposed. And then the resulting pattern would be shown on a screen, a photographic plate here, and the original beam would shine through. Some of the X-rays would go through unchanged, undiffracted, but there would be, it was found that there was a pattern of spots whose geometry reflected the geometry of the atomic lattice in a very interesting way. Now, von Laue analyzed this diffraction of X-rays by atomic lattices by looking at individual atoms in the lattice and how they interacted with the incoming X-rays. So he looked at each individual atom as an individual scatterer and added up the scattering that came from all the different individual atoms in quite a complicated calculation involving something called Fourier transforms, which you may have heard that term, but in any case, it's quite an involved calculation. And so his ideas didn't catch on, the analysis didn't catch on right away. But soon afterwards, the Englishman William H. Bragg and his son William Lawrence Bragg got into the act of X-ray diffraction, and they analyzed the X-rays diffracting off of not individual atoms, but off of planes of atoms. Okay, so if you imagine this top line of atoms here in this lattice as a plane, then an incident X-ray will come in at an angle given by theta from the horizontal, and it will reflect off of that whole plane of atoms at an equal angle theta, a lot like a pool ball hitting a rail and coming off at the same angle. And so, and then the incident plane wave could also come in and bypass the first layer of atoms and reflect off the second layer of atoms. And it would reflect off again at the angle, well, it would come in at angle theta and come out at an angle theta. So a total deflection of 2 times theta. But there would be a difference in the path length that the X-ray going to the second layer traveled compared to the layer, the X-ray traveling to the first layer. And that's because it's clearly traveling longer to get to the second layer. And if you look at it, if the lattice if the spacing between these layers is little d, which here is equal to big D is the spacing here, little d is the spacing between the layers that are acting as the scattering planes. If you look at this geometry, this length here would be equal to d. The sine of this angle theta would be equal to this length over d. So this length would be d sine theta, and there'd be 2 of them. So this second lattice plane would lag the first by 2d sine theta. And so this led to the Bragg diffraction law, which is that we would get constructive reinforcement between these 2 reflected X-rays off these planes and further reflected X-rays off of lower planes if an integral number of wavelengths was equal to 2 lambda d sine theta, because then we would get constructive interference. So this was a simplified analysis with lattice planes as scatterers, much simpler than von Laue's analysis, although yielding the same result. And this led to the Bragg diffraction law, n lambda is equal to 2d sine theta, where lambda is the wavelength of the X-ray, theta is the angle, well, 2 theta is the total angle through which the X-rays are being diffracted, and d is the spacing between lattice planes, and n is the order. So there could be several orders of diffraction. As you see in this picture here, there are several orders of diffraction in a given direction. Now, it makes it, we can see here that there are different types of lattice planes which can serve, different sets of lattice planes which can serve as these diffractors. So if the original one we had was called D1 here, that's the square lattice, so just the perpendicular lines. However, this set of lattice planes separated by D2 can also serve to reflect the set of X-rays, and D2, the distance is clearly less than D1. So that's going to set up a different set of angles for a given X-ray wavelength. And here's D3, which is every third, goes up 1 and over 2. And so there's whole sets of different lattice planes that can serve as diffractors in a given sample. And that's why we get this complicated pattern here. These are coming from different sets of lattice planes. Okay, so there's, practically speaking, there's 2 types of X-ray diffraction. There's single crystal scattering, which is what we were just looking at, a perfect atomic crystalline solid here. And then there's powder scattering. And in powder scattering, rather than a single crystal, we have a powder specimen, which is a bunch of small crystals jumbled in random order, or jumbled in random geometric arrangement. And because they're jumbled in this way, um, instead of uh, uh, instead of diffracting at only a given angle, they will diffract based on all the random orientations of these multiple powder crystals. They will diffract at the incoming beam by 2 theta um, around a ring. Okay, so around a ring. So it will diffract by 2 theta, but in any possible direction. So it'll produce a ring, and this is called a powder line. It's difficult sometimes to make single crystals, whereas powders are more easily made. So um, X-ray powder diffraction is often sufficient to um, to understand the structure of uh, of a substance. And this is a neat picture taken from our textbook. You'll have to look very closely. You might want to pause it and look. Um, that this top picture is an X-ray diffraction from a single crystal, and you can see the individual well-defined diffraction spots here. And then gradually more and more crystals are mixed in, and these diffraction spots start to blur and uh, turn into powder lines or rings, and then eventually we have a complete powder where we have rings where we used to have individual spots. Okay, so that's the difference between crystal and powder scattering. Now, X-ray scattering has proven to be extremely useful in understanding the structure of molecules, particularly in biology. Um, and the DNA molecule, in fact, which is pictured here, a computer rendition is pictured here, um, was its structure was actually determined in the 1950s using X-ray diffraction, this technique. So first, you can't scatter off of a single DNA molecule. You need to make a crystal, which is a real challenge, which is why someone won a Nobel Prize for it. Watson and Crick won a Nobel Prize for it. But once you make it into a regular crystal, which is an artist rendition is shown here, you can get diffraction patterns from these DNA crystals. And this is just one diffraction pattern from DNA crystal. This is a picture from our textbook. And just a quick story, Watson and Crick won the Nobel Prize, but the laboratory worker who took many of the DNA diffraction patterns and did a lot of the detailed analysis was a woman named Rosalind Franklin, who went unrecognized and probably definitely should have shared in the Nobel Prize, but that was a different era in physics. So the structure of DNA was discovered via X-ray diffraction. And now, in fact, many, upwards of 100,000 or so protein structures have been determined in a similar way by making protein crystals and scattering X-rays through them from many different orientations to determine the 3D structure of these proteins. And these are very complicated calculations that have to be done. All right, so de Broglie waves. So what do de Broglie waves have to do with scattering? Well, Louis de Broglie was a jolly, happy-go-lucky French nobleman who studied physics. And in 1924, he said he had thought that if light can act like both a wave and a particle, like light reflecting or refracting, reflecting off a mirror or refracting or off of through an interface, so like a wave or a particle, like in the photoelectric effect and black body radiation, like we've heard about, why not something like an electron? Now, an electron we know was thought of as a particle, and J.J. Thomson had analyzed his experimental results in terms of the electron being a particle, but no one had thought of an electron as being like a wave. But de Broglie had the idea that nature should have some symmetry like this, that both light, photons, and electrons should have wave and particle natures. So recall our relationship for a photon. We went through this a few classes ago, but borrowing from relativity, the energy of a photon is Pc, and c is the frequency times the wavelength. So that's from relativity. We also know from Planck and Einstein that the energy of a photon is hf, where f is the frequency. So we can set those energies equal, and we get p f lambda is equal to hf, since they're both equal to E. We can cancel the f's, and we're left with p lambda is equal to h, or solving for lambda, lambda is equal to h over p. Okay, so that was the formula that held for photons. And de Broglie suggested that since electrons have momentum, we could define a wavelength corresponding to the electron momentum through this same relationship, h over p. So just an example here, extending to the electron, a 1 kilo electron volt electron, converting, just to give an example of the wavelength we would get, kilo electron volt, 1,000 electron volts, converting to joules, we get this number. And then to get the momentum from the energy, we use this relationship that the kinetic energy is the momentum squared over 2m. And then solving for the momentum, we multiply through by 2m and take the square root. So it's the square root of 2m times the kinetic energy. So 2 times the mass of the electron times this kinetic energy. We get this number for the momentum of the electron. And then using this formula up here, the de Broglie relationship, we get that the wavelength of the electron is Planck's constant over p, which turns out to be about a few, on order of magnitude 10 to the minus 11 meters, or about the wavelength of an atom, which suggests that electrons are typically energetic electrons. 1 keV was a typically energetic electrons, would have wavelengths similar to those of X-rays. The one theoretical advantage of de Broglie waves was an explanation of Bohr's quantization condition. Remember, Bohr said that that angular momentum was quantized, that the angular momentum L was equal to n times h bar. And if you use de Broglie's formulation, the idea is that in the hydrogen atom, we have an orbit here, and the circumference of the orbit is 2 pi r. The idea is that since electrons now have wavelengths associated with them, that an electron should only be able to exist in that orbit if an integer number of wavelengths fit just so around a particular radius. So this is expressed by 2 pi r is n, where n is the number of oscillations here, times the wavelength. And we know that the wavelength is h over p. So we have 2 pi r is n h over p. And from that, we can get the angular momentum is equal to mvr, where p is mv. So r, the radius, times the momentum. But solving this equation here, if you can imagine bringing up p here, so you get p rp, and bringing down 2 pi here, we get nh over 2 pi, nh over 2 pi, or nh bar, which is indeed Bohr's quantization condition. So de Broglie, by suggesting that electrons have these wavelengths, was able to give the first hint of, at least suggestion of, a justification of Bohr's postulate that L is equal to nh bar for atoms. All right, so that was a theoretical argument, which Einstein found very compelling, actually. But electron diffraction from solids was actually, there was experimental evidence that was found very shortly thereafter, in 1928, a few years later. And Davison and Germer two American physicists set up an experiment where they took initially a nickel target, and they had a filament which boiled off electrons, a heated filament, electrons came off, and they accelerated the electrons up to a few kilo electron volts, and then came in and scattered off of the nickel target, scattered electrons, and they had an electron detector which could detect at various angles. Now, if the electrons were particles, and we know that the atomic surface of is not perfectly smooth, it's sort of rough, the electrons would come in and it would hit sort of a rough surface. So they would come in and come out at all different angles. And so we should get a uniform smear found by the detector, because the topography of the nickel surface would produce would produce electrons at a lot of different angles. And that's initially what was found. They saw that smear, and this is an interesting thing. There was a lucky accident. There was an explosion in their lab, which burned one of their nickel targets, and it fused the target into, which had been made up of a lot of small crystals, kind of like a powder crystal, of many orientations, fused it into larger component crystals, and that enabled a coherent pattern to be observed. So the actual result, once this accident happened and a essentially single crystal was formed of the nickel target, was a pattern that looked a lot like the X-ray diffraction we saw earlier, where there are certain preferred angles and positions for the detectors, just as for X-rays. These numbers here are code referring to the lattice planes, which serve as the scattering for the different X-rays. You don't have to worry about those, but that's part of the system for keeping track of the diffraction. So it turned out then that once we had a single crystal, electrons were behaving like waves, because in order to produce this, they had to be interfering with each other just like X-rays. And this was experimental support for de Broglie's idea, and the first idea that particles could have support for the idea that particles could have wave-like behavior. Finally, I want to go over the relationship between the Bragg scattering law for X-ray diffraction and the electron diffraction law, some geometry and trigonometry, but I think it's worth going through. This is the geometry of the electron diffraction right here, the electron diffraction of Davison and Germer. We have an incident beam that comes in, a scattered beam, and the angle between them is phi. The angle phi between this beam is, it's convenient to define that as twice alpha. So there's a bisector here, and alpha is half the angle of phi. And then, as in X-rays, electrons can scatter off of different sets of lattice planes. They don't have to scatter off of just the horizontal planes, but off of here, they're scattering off of this set of dashed planes. This set of dashed planes is separated by a distance d, okay, this little d here, and that set of lattice planes is at an angle theta to the incident beam, and also this angle right here is theta to the scattered beam. So meanwhile, the interatomic spacing itself, not between these lattice planes, but between the atoms themselves, is capital D. And we can see they're related by little d is equal to, so if we take this angle alpha here, which is why it's defined, then this angle here can be shown to be alpha as well. And so sine of alpha would be this lattice plane spacing d, little d, over the interatomic distance, big D. And so they're related by little d is equal to big D sine of alpha via the trigonometry of this triangle. Okay, so just a little bit farther. The angles alpha and theta make up a right angle. We can see that this is a right angle here. And so the sine of theta is equal to, which is equal to the cosine of 90 minus theta. That's a trig identity. But 90 minus theta, since they add up to 90, is alpha. So the sine of theta is cosine of alpha. So applying the Bragg diffraction to these set of planes, we have n lambda is 2d sine theta, that's Bragg diffraction. That's 2d cosine of alpha. This is alpha. Now, substituting in for d, little d, the lattice plane spacing is equal to the atomic spacing, big D sine alpha, which we determined down here, gives n lambda equal, substituting in for d here, to d sine alpha cosine alpha. So I've just substituted in big D sine alpha for little d. Then there's a trig identity that says the sine of 2 alpha is 2 sine alpha cosine alpha. And we can see what we have that here, 2 sine alpha cosine alpha here, times d. And the sine of 2 alpha is twice alpha is phi. So we just get n lambda is d times sine of 2 alpha, or d sine phi. And so this is the electron diffraction relationship. Now notice that there are multiple sets of lattice planes here, and so there can be multiple sets of angles phi at which the electrons are scattered. Okay, because there are multiple sets of lattice planes: the straight planes, the 45-degree angle planes, this sort of 30-degree angle plane, and so forth. Finally, we've been looking at cubic lattices, but it turns out, and this is a little bit beyond the scope of what we're doing here, but you may wonder if all materials are made up of cubic lattices. The answer is no, they're not. Most metals are made up of what are called either body-centered cubic, which have a cube with a atom in the center of the cube, or a face-centered cubic, which have a cube and an atom in the center of each of the 6 faces. And the analysis of the scattering of that is possible, though more complicated, for these so-called body-centered cubic BCC and FCC lattices. So in conclusion, both X-rays and through de Broglie's discovery that electrons can behave like waves, and electrons, as well as now actually neutrons, for some applications that are very useful, are now used as tools for probing atomic structures. And de Broglie's idea that electrons are waves served as the precursor for the wave function, which will be coming up, the atomic wave function, or the electron wave function, which will be coming up quite soon. So thank you for your attention, and I'll see you in class.